You've likely heard that certain non-stick frying pans are bad for your health. In the 1950s, pet birds actually died from the fumes released from these when cooking with high heat. Would it surprise you that the same class of chemicals are still an issue 70 years later today? Take a look at this list of questions and see how many you can tick off. Have you ever eaten microwaved popcorn? Worn a smartphone wristwatch? Cooked with a non-stick frying pan yourself? Now, not all brands out there are culprits, but for every yes you've answered on this list, you've more likely been exposed to perfluorinated compounds, or PFCs. PFCs are fluorinated alkyl chains touted for their chemical inertness, yet they take hundreds of years to break down and in the meantime bioaccumulate. For example, the average Canadian has 4 nanograms per liter of blood in their body. Ask yourself, did you consent to that? Good morning. My name is Kevin Golovin, and I'm a professor at the University of British Columbia. Today I would like to discuss why the world still uses PFCs and what my lab, and others, are trying to do about it. Perfluorinated compounds are unique in their ability to repel not only water, but also low surface tension liquids like oils, alcohols, and solvents that naturally spread and absorb into most real and artificial surfaces. This has left companies desiring oil repellent properties with a choice. Include these toxic compounds that can lead to birth defects, certain forms of cancer, and kill aquatic life, or forego the oil repellent properties. To understand liquid repellency, you must first understand wettability, the science of solid-liquid interactions. Since its inception in the 1800s, scientists have categorized surfaces by the contact angle that a liquid droplet adopts when deposited on a solid surface. If that liquid is water, materials are classified as either hydrophilic or hydrophobic, demarcated by an angle that is less than or greater than 90 degrees. PFCs are special in that they offer the highest possible water contact angles and are one of the few surface chemistries that don't result in complete wetting, or a contact angle of 0 degrees, with oils. For a liquid to be repelled by a surface, its contact angle must be much greater than 0 degrees. This makes oil repellency quite difficult. Over the last few years, however, my lab has been challenging these classical definitions. As the end user, you don't care about the angle that a water droplet makes when it's placed on your jacket. You care if you stay dry. And you don't care how a pizza delivery box repels oil, so long as the grease doesn't soak through the cardboard onto your pants, right? We realized that, so long as liquid droplets were highly mobile, they could be removed with ease, regardless of this pesky contact angle. That means we need to talk about a new term known as contact angle hysteresis. Hysteresis represents the energy barrier to droplet motion. It directly relates to the angle at which a surface can be tilted before a droplet slides off. Lower hysteresis implies easier droplet removal. A surface without hysteresis will essentially never get wet, and this is irrespective of the contact angle that liquid makes with the surface. This then begs the question, are PFCs best at minimizing hysteresis? Through years of study, both in my lab and others around the world, we would all argue, no, PFCs are not best at minimizing hysteresis. There are several methods for minimizing hysteresis that people have come up with, better than PFCs, but we've focused on nanoscale length films of covalently tethered polysiloxanes, or PDMS. These polymer brushes may be formed from either vapor or solution, and are interesting in that only one end of the chain is bonded to the surface. And because siloxanes are liquid at room temperature, the tethered polymer remains in a liquid-like state and retains many of its liquid properties. Functionalizing substrates with these PDMS brushes creates a unique surface that exhibits the properties of both liquids and solids. Importantly, the hysteresis on these liquid-like brushes is almost non-existent, and not just for water. In the bottom right of this slide, you can see that these brushes may be applied to many different substrates, such as metals, plastics, paper, and even toilet bowls. And the presence of surface texture, for example the UBC logo, does not degrade their performance. We've found that essentially all liquids slide off these hysteresis-free brushes with ease, and much easier than with PFCs. This opens the door to a host of different industrial applications where currently PFCs are in use. The image on the left comes from our report of the world's first PFC-free oil repellent fabric finish enabled by these liquid-like PDMS brushes. The SEM micrograph shows that a fabric midliner, in this case from Arc'teryx, the jacket company, has been rendered oil repellent by our PDMS brushes, and droplets of many different oils bead up and do not soak into this treated fabric, just like if they were treated with PFCs the way they are today. Outdoor apparel companies can therefore start to move away from PFCs without giving up their oil repellent properties by using these PDMS brushes on their fabrics. Grease-resistant paper is also a huge area where these brushes could have real impact. This video shows the most difficult liquid to repel in the paper industry's standard oil and grease resistance kit test. Not only do oils not soak into the paper, they slide off at the slightest tilt. Quite interestingly, oils are repelled by our silicone brushes, whereas they soak into regular, non-brush silicones. Oil repellent paper could also be folded into complex 3D shapes using origami, such as you're seeing in the top right. And this therefore could replace common well plates used in biological research today towards things like, for example, a COVID-19 vaccine. This makes our dependence on the petroleum industry less because we can start to use recyclable and biodegradable materials such as paper instead of plastics. However, any avenue where PFCs are currently in use can be disrupted by these liquid-like layers. The key insight is that if the polymer remains in a liquid state while still being bonded to the surface, hysteresis vanishes but the coating remains intact. Although the PFC-free future is bright due to these semi-liquid films, several challenges and open-ended questions still remain. The main challenge for these coatings, and any coating really, is durability. Unlike crystalline PFCs, these polymer brushes rely on just a single covalent bond to tether the entire chain to the substrate. There are no crosslinks or crystalline domains to aid in abrasion resistance. Finding a balance between their liquid-like nature and their mechanical resilience will be the key to their widespread adoption. And this will likely be application-specific. For example, perhaps a jacket need not be perfectly liquid repellent, as long as it can survive a dozen or so laundering cycles over the lifetime of the jacket. It may also be possible to improve the durability by increasing the number of bonds with the surface, but how this will affect the liquid repellency of the brushes remains to be seen. In general, in terms of the unknowns, we don't know a lot about the specific structure, orientation, or even what we fully mean by exhibiting a liquid-like nature. For example, what if both ends of the chain bond to the surface, forming a liquid-like loop? Do loops offer enhanced properties compared to linear chains? And how does molecular weight affect the adhesion of both solids and liquids to the PDMS brushes? Eventually, entanglement will become dominant, but what effect, if any, does the length of the chain have on the liquid repellent properties? And do other amorphous polymers well above their glass transition temperature, such as, for example, polyethylene, polyethylene glycol, or perfluoropolyethers offer similar liquid repellent properties? And most importantly, what does it even quantitatively mean for something to be like a liquid? Are there rheological, fluidic, or viscoelastic similarities with actual liquid films? And how does the chemical and physical structure of the brushes affect this liquid-like nature? PFCs will thankfully be phased out of production worldwide in 2023. PDMS brushes offer an alternate route to oil repellency, a property not seen for traditional silicone surfaces. However, durability is going to be the key to their widespread adoption. Overall, while the properties of these liquid-like coatings are both rich and quite deep, at least in my opinion, we've really only scratched the surface of what we can actually do with these liquid-like films. I'd like to end by thanking my wonderful research group, along with the generous funding support from both industry partners and the Canadian government. And thank you for listening.